Hello, welcome to this video. So in this video we're going to be looking at virtual particles. We're going to be looking at how quantum mechanics allows them to be produced and also their essential masses, where we'll be using full momentum to understand how we calculate a kind of mass of a virtual particle, and the mass tells us a lot about what the virtual particle is doing. So this video is going to start with reviewing the idea of full velocity, such that we can get to a full vector called full momentum. And it's full momentum that relates the energy and 3D momentum of a particle or object together in terms of the mass of that object. So that's why we're going to start with four vectors to get an equation for mass, and then we're going to use it to understand virtual particles. So we're going to begin with four vectors and relativity, and at the end bring in a little bit of quantum mechanics. Now, virtual particles are very important in terms of transmitting forces, because in classical physics we kind of assume that there's a potential that particles can generate, and that's how they influenced the behaviour of other particles. But in terms of quantum field theory, we have to quantize this potential, and the way that we do this is by considering the potential as really the result of the regular production and annihilation of a group of force-carrying particles. So essentially the creation and occasional destruction of these force-carrying virtual particles. So if we think of an electron, for example, by itself, it's generating an electric field, and therefore we can think of it as surrounded by a sea of virtual photons, as an illustration has been shown here with this orange-red orb representing the electron and these tiny dots representing the virtual particles around it. We understand how virtual particles appear by using uncertainty principles in quantum mechanics that allows energy to fluctuate, such as we can see in the diagram where we have those kind of patches of blue and other colours in a grid. This shows kind of the energy fluctuations in a ground state quantum field. Now, this video isn't really about quantum field theory, but quantum field theory gives us a new way to think about forces in terms of the creation and destruction of virtual particles, and that's really the motivation for studying them. And so in this video we'll look at understanding the masses of virtual particles and what they're doing, but starting with getting an equation for mass that we can apply to them, and we'll get that through looking at a new four vector that we haven't looked at yet in this playlist called four momentum. So momentum is related to the velocity something is moving at, because classically we think of the momentum as equaling mass times velocity. So to get to full momentum we're going to need full velocity. Now, I covered full velocity on the previous video, but as a revision and also as going through some material if people are starting the playlist at this video or are completely new to the channel, we, all the way back in the introduction to kind of relativity, began really with describing space-time and talking about the position of something that occurs in space-time as a point on that space-time. So a point represents a location and a time where something might occur. And so if we have, let's say, a car that's moving in space, well, it's moving in space and it's also travelling with you into the future, so it also in some way has motion in time, and we describe that as kind of the change in the forward position of the object. So the change in where it is in space-time. Now, the first component, which has the index 0, is our time-like component. So in the context of forward position, that's a measure of time passing. And our kind of final component is kind of a space component, telling us, where that moving object, where that moving car is in space. And if that car is just moving along one spatial axis, we only need one component for that. And that component has an index of 1. So x0 is our time-like component and x1 is our space-like component. But we can put time-like and space-like components together to get forward position and then track how that trajectory changes across space-time, which is our purple bulk line shown there. Now, for momentum is going to be a kind of measure of the momentum of a particle through space-time, which would be equal to the mass of the particle times its velocity through space-time. So to get full momentum, we need some measure of velocity through space-time. And we covered that velocity, forward velocity, on our previous video, but here's just a quick recap. So, forward velocity is defined to be the rate of change of forward position, so how quickly this orange curve is changing throughout space-time, but with respect to proper time. Because in relativity we can't just say the rate of change, because how quickly time progresses depends on the observer, and therefore we have to pick a reference frame when describing time, and we use proper time. So forward velocity is the rate of change of forward position, but where that rate is measured in terms of proper time. And three important aspects of forward velocity are firstly the definition. It's the rate of change of forward position with respect to proper time. That tau, that curly t, is the proper time. Also, given the components we had for forward position, when you differentiate forward position with respect to proper time, you'll find the components of forward velocity, and therefore you'll find that forward velocity u is equal to gamma lots of c comma v. And the fact that v refers to the speed of the moving object whose path through space-time is being shown by the purple line, v refers to the velocity of that moving object through space, and v is the space-like component of forward velocity. Some people say, well, c is the time-like component of forward velocity, so it's how quickly you move through time, leading people to say you move at the speed of light through time. Although personally, I don't think that statement in and of itself makes much sense, because, there's a lot of maths that goes on, really, to get from the definition of forward velocity to its components. And so I just because c is in the first component of forward velocity, it doesn't mean we move through time at the speed of light. For example, if you bring gamma back into these brackets, then you could say we move it through time at the speed of gamma times c or something, So, but the important thing is that forward velocity is given by these components here. And when we found the size of forward velocity, we found that was equal to the invariant quantity of the speed of light, although that wasn't a massive surprise, because we know already the founding principle of relativity is that the speed of light is Lorentz invariant, or in other words, any observers, providing they're moving at constant velocity, will agree on the speed of light no matter what a given observer's velocity is. So we went through full velocity quite quickly, but that's because we covered it on a previous video, so it's mainly a recap. Now we're going to go from full velocity to full momentum, which will help us understand the link between energy of a particle, its momentum through space, and also the mass of the particle in the context of relativity. So in space, the momentum is equal to mass times velocity, and I'll put arrows above momentum and velocity because they're vectors. They have size and direction. But the key thing is that in 3D space, momentum is mass times velocity, so it kind of follows that it's natural to say that in 4D space-time, full momentum is equal to mass times full velocity. And using our expression we had for full velocity on our previous slide, we can therefore get that full momentum is equal to gamma times m, lots of c comma v. And here I'll just put the gamma into the brackets. Now here you do want to bring the gamma into the brackets because each of these terms here have independent physical significance, but that significance relies on the gamma being part of the term. So if we look at the first term of our full momentum, which has an index of 0, so if we look at P0, well, P0 is gamma times mc, where gamma is the Lorentz factor. And what physical thing kind of looks like gamma mc? Well, we know from our video on proving E equals mc squared that the total relativistic energy of a particle is equal to gamma mc squared, and therefore gamma mc is just the total relativistic energy E divided by the speed of light c. So gamma mc is just the relativistic energy divided by the speed of light. Now for the second component of full momentum, well, we have gamma mv, but on also the video where we looked at deriving E equals mc squared, we saw that we can define the relativistic momentum to be gamma mv, because a particle behaves in terms of its resistance to acceleration as if it has a relativistic mass gamma m, and therefore the natural relativistic velocity would be the natural relativistic momentum would be gamma mv, so relativistic mass times velocity. Now, I talked about relativistic energy and relativistic momentum on the E equals mc squared video, so I'm not going to kind of talk too much about them here because there's already a video on that which covers these things. But we've got kind of like the components of full momentum. We can already see that these components contain mass, indicating that the size of full momentum might have something to do with mass. And given we understand physically now what the components of full momentum are, we're going to find the size of full momentum, which will give us a Lorentz invariant, and it will turn out that that Lorentz invariant is going to be proportional to the mass of the particle with the full momentum we're describing. And it's worth saying that, when we say Lorentz invariant, to emphasise again, we mean it's a value different observers will agree upon no matter the relative velocity of those observers, providing they're not accelerating. So, in other words, we'll see when we observe that the Ras mass m of an object is Lorentz invariant, we'll mean by that, if you say that the Ras mass of a cup is 2 kilograms when you're sitting next to it drinking, you'll also agree it's 2 kilograms if you were going to observe it when you were, say, out running with your dog or something. That's what we mean by Lorentz invariant. So we now have an expression for momentum and its components. We also have reviewed the expression for velocity and its components. We're now going to have a look at Lorentz invariant quantities. So to kind of recap, a full vector has a Lorentz invariant quantity associated with it. So a quantity is kind of Lorentz invariant if different observers who may be moving relative to each other still agree on that quantity, even in the context of special relativity. So when we looked at the full vector of full position, we saw the associated Lorentz invariant quantity was the distance between events in space-time described by the space-time interval. And exploring this led to ideas like time dilation and indirect applications of time dilation, like ultimately leading towards E equals mc squared, the equation that relates mass and energy. And its energy associated with less mass. When we looked at for velocity in our last video, we saw the Lorentz invariant quantity was the speed of light for a vacuum, c. And we would kind of expect that because the founding principle of special relativity is that the speed of light is Lorentz invariant. And now we're going to look at the Lorentz invariant quantity associated with full momentum. So as full momentum is a full vector, there is a Lorentz invariant quantity associated with it. Now one might be tempted to do the usual process to find the size of full momentum squared, which will be essentially the Lorentz invariant quantity we're looking for. Because essentially a quantity is Lorentz invariant because it in some way measures the size or the length of a full vector, and different observers in special relativity agree on the length of the full vector because the only difference from one observer and another is the angle of their space-time axes. So they might measure different components for the full vector, but the length of the full vector will remain preserved even when we're looking at a different observer. So the length of a full vector is naturally a Lorentz invariant quantity. So here we have an expression saying that the size or length of full momentum squared is equal to the time-like component of full momentum squared minus the space-like component of full momentum squared. And we get that through taking the scalar product of full momentum with itself in the context of space-time. And to do it in the context of space-time, we need the Minkowski metric, which is that symbol with 2 low indices. Now, if you're unfamiliar with the Minkowski metric and scalar products in space-time, there's a video earlier on in this playlist, or kind of there's plenty of good material also online and plenty of good documents, or for this video we can kind of run with the size of a full vector squared is equal to its time-like component squared minus its space-like component squared. Now for this video I'm going to represent the size of a full vector by having a pair of parallel lines, a symbol for the full vector, and then another pair of parallel lines. And that's just kind of general practice how it's done. In past videos I've used the symbol Q because it's just easier having a single letter to represent something. I feel it makes it more approachable. But in this video we're going to have multiple Lorentz invariant quantities we're worried about. So having multiple Q's with different meanings at different points would just get really confusing. So I'm using the more conventional notation in this video for the size of a full vector. Now, whilst the expression we have for the size of full momentum is kind of great, and we'll use it to understand the dynamics of kind of particles in relativity, and we'll also use it to really understand virtual particles in the kind of second part of this video. For now, this isn't a brilliant expression because it doesn't really help us go anywhere, because due to what the time-like and space-like components of form momentum were, it's not really clear what the time-like component squared minus the space-like component squared would be. Like, it's very hard to move on from this point if we're going to try to calculate the size of form momentum directly, and therefore find the Lorentz invariant quantity associated with form momentum. So what we do is we try to go via a method of using a 4-vector we're already familiar with, which has a much more naturally intuitive size, and try to use this to help us. Well, a vector associated with form momentum that has a very intuitive size is for velocity, which, as we said, has a size equal to the speed of light. And the speed of light is the founding kind of idea of relativity, so it's very physically significant. So let's think about form momentum in terms of form velocity. Well, if form momentum is defined to be mass times form velocity, then logically it follows that the size of form momentum should equal the mass, the Rass mass of the object whose form momentum is being described, times the size of form velocity. Now the size of form velocity is just given by the scalar product of the form velocity vector with itself. The square of the size of form velocity is just given by taking the scalar product of form velocity with itself. And then using the components of form velocity that we had before, and bearing in mind that the scalar products of form velocity with itself would just yield the time-like component of form velocity squared minus the space-like component of form velocity squared, we end up concluding that the size of form momentum squared will just be equal to gamma on Lorentz vector squared times the Rass mass squared times by c squared minus b squared. And if you use the definition for the Lorentz vector, kind of found it earlier in this playlist, or also kind of available online and in documents and in any book on special relativity, this kind of Vari expression involving the Lorentz vector in our bottom equation can be simplified down, and we end up with concluding that the size of form momentum squared is mass squared times the speed of light c squared, and simplifying this by just square rooting both sides, we get that the size of form momentum is just mass times the speed of light. So it looks like the Lorentz invariant quantity associated with form momentum is the Rass mass of our object times the speed of light. But it's not very clear how to physically interpret this, like what is Rass mass times the speed of light? We would really like to say that Rass mass, which has a much clearer physical interpretation than Rass mass times speed of light, we would like to say that Rass mass is the Lorentz invariant quantity. Now, can we do this? Well, because time c is Lorentz invariant and c is Lorentz invariant, it's the Lorentz invariant quantity associated with form velocity, m would have to be Lorentz invariant, because if m wasn't Lorentz invariant, then even if c was, then m times c wouldn't be. So to have m times c being Lorentz invariant, c to be Lorentz invariant, m must also be Lorentz invariant. So in that sense, in a general sense, Rass mass is associated, associated Lorentz invariant with form momentum. Now it's worth saying, occasionally when you hear Lorentz invariant, you might also hear the word Lorentz scalar. The reason being is we define a scalar to be a quantity which doesn't change when you change the coordinate system. So for example, the temperature of tea when I'm drinking it, and now as we're approaching winter or getting towards that, it's getting colder, I am drinking tea more often, so tea is on my head a fair bit. So, a mug of tea, it has the same temperature no matter what coordinate system I use to measure where the tea is relative to me. In that sense, the temperature of the tea in the mug is a scalar. Now, similarly, we said that a Lorentz invariant quantity is associated with essentially the length of the full vector being preserved even when we jump observers, so even when we look at changing the angle of the space-time axes, or if you like, the space-time coordinate system. So in this sense, a Lorentz invariant is just something that acts as a scalar under Lorentz transformations. So we call such an object a Lorentz scalar, to just bring those two ideas together. So we could also say that Lorentz mass is a Lorentz scalar. But we would really like to say not just that mass is a Lorentz scalar associated with form momentum, we'd really like to get rid of the C completely and just go, well, the size of form momentum is literally equal to the Lorentz mass m. But to do that, we have to get rid of C. Now, another reason we really want to get rid of C is because we can combine the top equation, namely rocks, and the bottom equation, and doing that will allow us to relate the relativistic energy, the relativistic momentum through space, and the Lorentz mass of our particle. But at the moment, if we do that, we'll have loads of factors of the speed of light c raised to various powers due to our kind of components of form momentum. And we don't really want loads of c's floating around to different powers, because that hides a lot of the physics. So to both say that the size of form momentum is equal to Lorentz mass, and also to be able to have a clear and clean expression relating relativistic energy, relativistic momentum, and Lorentz mass, we want c's to vanish, and that's what we'll look at doing in the next slide. But to get to that beautiful equation we're looking for relating relativistic energy, relativistic momentum, and mass, we're going to simplify things a bit. Because one thing you might have noticed is that the speed of light c is coming up a lot when we look at form momentum. It's coming up in the time-like component, and it's also coming up in the size of form momentum. So really we want to, in some way, remove c from our expression, because otherwise we have tons of speeds of light raised to various powers, and it's going to make everything look quite confusing. The other reason for doing this is if we want to apply, as we will want to, our relationship between energy, momentum and mass to virtual particles, then we want to have our equation in a form which makes it easy to use in quantum field theory. And in quantum field theory, they get rid of the speed of light through doing essentially a very similar process to what we're going to do now. So this will be about removing our pesky c's from our equation. I call them pesky because whilst in some cases they're useful, in the case of form momentum, and definitely relating mass to form momentum, they actually disguise the physics of what's going on. I mean, we've already seen that the Lorentz invariant of form momentum is technically mass times the speed of light, but really, because c is Lorentz invariant, mass is Lorentz invariant, so we might want to say that the size of form momentum is just equal to mass in some way. And we can do that if we use this following procedure. So, to get rid of our c's, we note that c is a constant, first and foremost. In special relativity, it's a constant, and it's defined by more fundamental constants describing how easy it is for the electric and magnetic field associated with light to travel through empty space. So C is a constant, and that means it's not a variable, and so its value doesn't change, it always has the same value. And therefore, we can just set C to equal, any size we want to, and for example go, well, the light moves at, for example, 1 light second per second. In other words, 1 unit of distance per second, but where that unit is a light second. We can do that. Essentially, if something has a constant size, a constant value in physics, well, providing you change the value of everything else accordingly, you can set that original value to whatever you want. It's only if something is changing where you have to be a lot more careful. But we can be even more radical than setting the speed of light equal to 1 unit. We can go, well, actually, what matters in physics is that units are consistent with each other. We don't really care about what does or doesn't have units. And since C is a constant of nature, we can easily just treat it like a constant of nature with no units at all, in much the same way that pi is, if you like, a constant of Euclidean geometry. Whenever you're doing Euclidean geometry, at least if you're dealing with curved objects like, like ellipsoids or spheres, you will see pi pop up, and pi doesn't have any units. Now we can do a similar thing with C. We can just go, well, C is, if you like, describing the geometry of space-time, and we don't have to give it any units. We'll have to change the units of other things accordingly, but it's entirely physically allowed to go, well, C doesn't have any units at all. So, in short, C has a size of 1 and it has no units. Or at least we can work with that. So we can just say C is equal to 1. Literally the number 1. And we can do that, and that gets rid of our factors of C, because 1 raised to any power is just equal to 1, and something times 1 is just itself. So, suddenly we can ignore factors of C altogether. And that simplifies things a lot. And so now we're going to take C equals 1. And what that will mean, for example, is that whereas before we had the time-like component of form momentum was equal to the relativistic energy divided by the speed of light, now because we said C equals 1, we can just go, well, the time-like component of form momentum is just equal to the relativistic energy. So, for example, it simplifies things there, and also we can go, well, the size of form momentum is just going to equal mass, because before it was mass times the speed of light, but again we set C equals 1. So, it simplifies things a lot setting C equals 1, and I will do this for the rest of the video. So, now we're going to gain an equation of motion, if you like, or at least something that relates energy and momentum together through mass. So we're going to essentially rewrite our equation for the size of form momentum. So before, remember, we said that form momentum squared, the size of it squared, is equal to time-like component squared minus space-like component squared. But we've also now done something where we said C equals 1. And what that means, as mentioned on our last bit of the video, is that the time-like component of form momentum now equals the relativistic energy of our particle, or object with the form momentum we're describing. but as before, the space-like component of form momentum is still just equal to the relativistic 3D momentum, i.e. the relativistic momentum of an object through space. And if we now substitute our expressions for P0 and P1, so the time-like and space-like components, we get, remembering also that the size of form momentum squared will equal mass squared, we'll get that relativistic energy squared minus relativistic momentum squared is equal to mass squared. Now, due to special relativity, through which we've derived this equation, all kind of like particles which are at least permanent features of the world, so not a result of quantum uncertainty, will obey this kind of correlation, this connection between relativistic energy, relativistic momentum and mass. Now we're going to, on the next slide, explore what this means and kind of visually try to understand this equation, and then we'll be applying it to virtual particles to see why, although we can in a sense use this equation if quantum mechanics comes into play, we get some very, very strange masses. But that's what we're coming on to soon. So now we're going to try to geometrically understand the equation we had before, linking energy, momentum, and mass. Well, it's worth saying, essentially what we have is saying that, okay, well, different observers might disagree on the components of form momentum, so they might disagree on the relativistic energy or relativistic momentum of a particle, but they will agree on the size of form momentum. And a way to kind of change the components of a vector but keep its length preserved is to rotate the vector around a given point. Now, in Euclidean space, this would end up forming a circle or a sphere if the vector lived in three-dimensional space. But because our vectors live in space-time, actually when you rotate them around all possible angles but keep their length preserved, you end up with something that to us looks like a hyperbola. So a hyperbola is kind of like a space-time version of a circle. And so here we have our equation linking the time-like component, the space-like component of form momentum and mass. And as I say, this essentially describes, well, if we keep mass fixed, so if we keep the size of momentum fixed, then any pair of relativistic energy and relativistic momentum values that satisfy this equation will end up describing a vector that lives somewhere on this space-time version of a circle, with, if you like, a space-time radius equal to mass m. I put radius in quotes because the notion of a radius is strange in space-time thanks to its hyperbolic geometry. But since, in a sense, a 4-vector, well, if we have a 4-vector, and we consider what that 4-vector looks like in all possible reference frames, we end up forming a space-time version of a kind of spherical surface, although it would be a hyper-surface because it would be like a sphere in 4 dimensions. Because of that, we can kind of think about all these kind of like vectors as essentially having their final tips lying somewhere on this hyper surface, on this kind of, spherical surface but in 4 dimensions. and space-time. And so, in that sense, we say that kind of like, if you like, the four vectors for momentum are, for a fixed stem, are kind of forming, if you like, if you look at the tips of those vectors, forming a kind of thin shell, if you like, spherical shell. So we say that kind of particles which obey this relativistic equation relating energy, momentum and mass lie on the mass shell. We say mass shell because it's mass that determines the radius of this shell, and we say shell because essentially all these four vectors live on this shell if we keep the mass fixed. And the shell is like a spherical shell, or the space-time version of one. Now that might be hard to visualise, but that's why we use the term on the mass shell, which might sound really bizarre when looking at this equation that looks like a hyperbola, but actually a hyperbola is just just what a circle in space-time looks like to us, because we're thinking in terms of Euclidean space. But now we've discussed what the term on the mass shell means, we're going to look at particles that are not on the mass shell, and this is essentially virtual particles. It's one way to define virtual particles. So we mentioned the idea that due to special relativity we expect long-lasting particles to lie on the mass shell, and you might wonder, well, if every particle in the universe is obeying special relativity or principles therein, how could the universe possibly end up with particles which do not lie upon the mass shell? And the way the universe gets around the mass shell restriction, if you like, is through quantum mechanics, particularly ideas of superposition and uncertainty, which kind of surround the realm of quantum mechanics and are computationally understood if a little ambiguous as to what their metaphysical meanings are. So in quantum mechanics, an object can act like it kind of has many classical states simultaneously. It can kind of act as if it's in a superposition of classical states. Now, classical states are kind of descriptions of a quantity, where those descriptions are kind of based on observables we might look at in classical physics, so things like energy, momentum, mass. When we look at neutrino oscillation, we're talking about superposition in terms of mass. We also have angular momentum, and position. Common classical states, but due to quantum mechanics, an object can actually exist for any one of those states as if it has multiple values of that state simultaneously. It kind of acts like it's smeared out over classical states. And we represent this by thinking about how the probability density associated with a particle being in a particular classical state when we measure it varies across the kind of classical states available to that particle. So, for example, if a particle was acting classically and was not in superposition, so was in one very clear state, then all the probability would be kind of like squeezed into that particular classical state, and there'd be no probability anywhere else. So if we look at the probability density function, we would see a spike at that kind of classical state. However, quantum systems don't behave like that. They behave as if their probability density is spread out over the possible classical states. And the common situation when we do this is in chemistry. So chemistry is based on essentially the properties of molecules, which come from the properties of atoms and how atoms interact, particularly the electrons in the atoms. And the electron in an atom actually has a probability density which, even if it's just kind of occupying a single atom, is actually spread out across the atom, as we can see here. Now it's spread out kind of symmetrically, resulting in this lovely kind of symmetrical, almost petal-like shape, because there's a radial attraction to the nucleus which is holding the electron to the atom. And that generates symmetry within the potential the electron is feeling, the electrostatic potential, which is then reflected in the wave function and therefore the probability density. But we can see how the probability density is spread out here. Now there's three numbers, 4, 3 and 0. 4 refers to the energy of the particle, so this is in the fourth energy level. 3 and 0 refer to the angular momentum state of the electron. We have two, unlike in classical physics, we can't define the angular momentum exactly, but we can define it well enough that we can give exactly two numbers describing the angular momentum state of the electron in an atom. So 3 and 0 will tell us about the angular momentum state, or we can think of it as two separate angular momentum states if you want to. But essentially, the electron here has well-defined energy. Well, as close to well-defined angular momentum as is possible in quantum mechanics. But it clearly doesn't have well-defined position because its wave function or the relative probability distribution is spread out across the position states. We don't have a spike. We have a lovely kind of really pretty looking petal-like pattern. And we're saying we get a pretty petal-like pattern because we have a number 3 there. As you increase that middle number, the patterns start to become more and more exotic, shall we say. But that aside, in an atom, electrons obey superposition, but also particles, as they're moving through space and interacting generally, can enjoy quantum superposition. Now, with an atom, we're generally talking about electrons, at least when we're not worrying about covalent bonds or things like that. We're talking about electrons in well-defined energy levels, but with uncertainty in their position. However, for our purposes, we're going to be interested in particles where the uncertainty is not in the position, it's in the energy and the momentum. So a quantum particle can be in energy or momentum superposition state, and this leads to natural uncertainty with what energy or momentum will measure the particle in, because we don't know what classical state we'll find it in if it's initially in a kind of mixture of different values for that classical state. So, in other words, particles can act like they don't have well-defined energy or momentum, like their energy or momentum has somehow kind of smeared. And because of this, whilst the kind of like energy of well, the expectation energy of a particle and the expectation momentum for the particle might enjoy a relation putting the particle on the mass shell in terms of like the average momentum force vector, if you like to think of it like that. If we look at the force vector at any moment in time, and we're not taking averages, then there's actually no reason due to this uncertainty to expect the energy and momentum of a particle to be related in such a neat way that we get the rest mass of the particle. Because the energy is free to divert from the average or expectation value as is momentum such that the connection between energy and momentum no longer gives us a Ras mass. Due to the units involved, it will still produce a mass, a kind of effective mass for a particle at that kind of small interval in time, but it won't necessarily refer to the Ras mass anymore. And this leads to particles generally being allowed to be off the mass shell. If we take this to an extreme, we can even have particles whose entire energy and momentum correspond to uncertainties in energy and momentum states of quantum fields, and that will lead us to the idea of virtual particles. Now it's worth saying for the energy or momentum of a particle, which is kind of obeying quantum mechanics, and therefore has some inherent uncertainty associated with it, I put subscripts Q and R. Q to remind me quantum mechanics is involved, R to remind me relativity is involved, but yeah, that's just my personal choice. But because in this video we started with a Ras mass, and now we're dealing with effective mass, I find it helpful to put subscripts here to help us differentiate clearly. So M with the subscript Q and R is the kind of effective mass of our particle, which is free to be different from the Ras mass. Generally it's not going to be wildly different, as in drastically different in magnitude, but it is free to be different, and sometimes it might be drastically different. And as I said, it's this idea of off mass shell kind of for momentum and therefore energy and 3D momentum states being possible, which leads to the idea of virtual particles. So that's what we'll talk about kind of like for really the remainder of this video before we wrap things up. So we mentioned that there are particles whose full momentum can cause them to be off the mass shell. We're now going to have a look at a kind of like particular special class of particles whose whole existence is due to quantum uncertainty, allowing essentially full momentum to lie off the mass shell. And this group of particles is called virtual particles. And to talk about virtual particles, I need to briefly, in a fairly linguistic and poetic way, talk about quantum fields. Now, quantum fields are the fundamental constituents of the universe. They're kind of what everything is ultimately made from, in that even particles, or fundamental particles, are kind of like excitations or manifestations of kind of really excited quantum fields. So ultimately quantum fields underpin everything, every interaction, every presence of matter. And these quantum fields pervade all of space and time. Now these quantum fields can be really excited at particular locations in space-time. For example, where you are, kind of at the current time, the kind of quantum fields are really in a very excited state because there is so much kind of like matter and energy in the form of matter and radiation where you currently are, because you are made up of lots of particles. So the quantum fields are in really excited states. But the other extreme of that is these quantum fields can be in the ground state, the lowest energy state possible. And when they're in their ground state, they're dynamical, they're evolving. At least we assume they're evolving, because we assume them being in their ground state doesn't cause them to suddenly obey different equations of evolution than when they're in excited states. At least fundamental dynamical equations. But when they're in their ground state, to all physical intents purposes, these quantum fields have zero energy. At least if it's not for kind of quantum excitations, these quantum fields have zero energy. So there's literally no energy present in these quantum fields for them to create particles. However, due to kind of fluctuations allowed by quantum mechanics, a field, even in its ground state, can fluctuate, and from that fluctuation can emerge or essentially manifest virtual particles. And if the quantum field in its ground state is the electromagnetic field, then when it starts to, if you like, ripple, if we could use visual language, or, you know, more technically, if it starts to fluctuate, then virtual photons will be produced. Well, photons are the kind of force-carrying particles for the electromagnetic field. So a virtual photon is essentially created due to the uncertainty principle in quantum mechanics, but applied to the electromagnetic quantum field. It's essentially a manifestation of the field kind of like undergoing oscillations due to uncertainty principles within quantum mechanics. And if we're going to understand what the motion, if we're going to understand the properties of this virtual photon, we have to look at kind of particular interactions this virtual photon could be involved in. And in this video we'll look at a couple. So we're going to start with essentially electron-electron repulsion. Now classically what we would think is that we've got two electrons, and these electrons have an associated electric field. So if we fired them from two electron guns close together, they would get close together, but then they would lose energy, and due to their kind of repulsive electric fields, they would then be pushed apart. But at the start of the video we mentioned that in quantum mechanics or quantum field theory, we replace the idea of a potential with the idea of there being lots of virtual particles around these electrons. And so really, if we're thinking fundamentally in terms of, you know, almost model understanding of what's going on in kind of a repulsion between charged particles, we need to think of it in terms of the exchange of virtual photons. So the way that we think of repulsion now between these two electrons is we've got two electrons coming towards each other. And because in this diagram here called a Feynman diagram, we've got time, in this case in the vertical axis, and space on the horizontal axis, when they're approaching each other, they're kind of travelling diagonally upwards, but towards a point in space, and they're going upwards because they're moving forwards in time. And then they get close enough together for there to be a high probability of one electron kind of like exchanging a virtual photon with the other electron. So one electron, if you like, emits a virtual photon, and then the other electron absorbs it. And if you think about momentum conservation, this would then cause the electrons to move off in opposite directions after this exchange of the virtual photon. And therefore we get the effect of electrons repelling, but without need to talk about any, you know, electric fields. We can just do it solely in terms of photons, and in this case the virtual photon exchanging momentum between one electron and the other. And also an interesting thing to know about this virtual photon represented by a squiggly line in our Feynman diagram here showing the particle interaction is that the squiggly line doesn't have any net motion upwards or downwards, so it looks like the photon isn't really travelling into the past or the future. And the reason for that is because this virtual photon is produced by energy fluctuations in the electromagnetic quantum field. But associated with the energy fluctuations, or the uncertainty in energy, is uncertainty in time. And what this means is, for this photon, it's really unclear, how time flows. It's not at all clear that the photon would even perceive a linear flow of time, because there's uncertainty in time, and it's kind of inherent. So what time looks like for this virtual photon is still something that is currently being attempted to be understood. I mention that as a side note because, part of my motivation for making this playlist on special relativity was, my fascination for time, so I thought it was worth mentioning. But also, for others of you who are watching the playlist and are intrigued by time, worth mentioning the strangeness of time for virtual photons. But if we're going to calculate the mass of this virtual photon, it's a factor mass, which, remember, doesn't have anything to do with the rest mass of the photon, nor does it have anything to do with kind of invariant quantities in special relativity, but it will have a lot to do with what the photon is actually doing. So in this instance, the photon is attempting to exchange momentum between one electron and the other. So clearly it has momentum, and there's no reason to assume it would have anything but real momentum, in which case momentum squared is going to be bigger than zero. The photon is behaving in a way that is consistent with this. It's essentially the role of the photon to have kind of, a momentum where the momentum squared is bigger than zero. So we've got the momentum, but we now need the energy of our photon, and then we can use the energy and momentum to get a notion for the effective mass of this virtual photon. So if we look at the energy of our photon, well, here's the interesting thing, really. So our photon is kind of like, it is interacting with our two electrons. But if you look at kind of like repulsion between electrons, if the electrons kind of move symmetrically, so let's say that they moved towards each other and are kind of attempting to get a dead-on collision and then repelled, then after the repulsion, the energy would still be equally distributed between the electrons if it was equally distributed before they repelled. Now that wouldn't happen if the photon had energy, because if the photon had energy, then after kind of like the exchange of the photon, one electron would have lost energy and the other electron would have gained energy, which would break this imbalance. And therefore, clearly this photon can't be exchanging energy. It can exchange momentum, but it can't exchange energy. And so the energy of this photon is zero. And this is a really strange thing for a photon, because remember, for real photons, as they're called, so in other words, photons associated with quantum fields which are naturally in excited states, so whether in excited states, without worrying about quantum fluctuations. For those kinds of real photons, as they're called, they have momentum by virtue of having energy. But for this virtual photon, it has momentum, but it has no energy. So virtual particles are very, very strange. But anyway, now we've got an expression for momentum and energy, we can put them together to get an idea for the effective mass of this virtual photon. So, remembering p squared is bigger than 0, e is 0, and then using how they relate to m, the effective mass of our virtual particle, we see that m squared is going to have to be less than 0, implying that m is imaginary. M is the square root of a negative number, and so it exists somewhere, on the complex plane. And so we have a photon with imaginary mass, and this is a very genuine thing, but it's worth saying this imaginary mass is not mass in the usual way we would think about mass. It's actually just describing what the photon is doing. It's saying this photon is causing scattering and therefore is transferring momentum without transferring energy. That's what the imaginary mass means. But you might wonder, well, do all virtual photons have imaginary mass? The answer is no, and we'll look now at another interaction between particles using a kind of similar Feynman diagram, but where we'll see a role of a virtual photon where the photon won't have imaginary mass. Hello, so we've seen in the last slide that we have photons with imaginary mass referring to scattering, whereas for virtual particles the effective mass really tells us what the particle is doing. It doesn't tell us anything about the Ras mass associated with kind of, longer lasting versions of these virtual particles. So, remembering a virtual photon is created due to the uncertainty principle in quantum mechanics, but essentially applied to quantum fields. And here's a Feynman diagram. Now that Feynman diagram may look similar to the one before, but a key thing here is now we've switched the order of the axes, so now distance is our vertical axis and time is our horizontal axis, but we haven't altered the way that the diagram looks. But by switching the axes but keeping the diagram the same, this diagram is now describing something different. So, working with what we have here, if we start from the left and go to the right, we have particles which are, going towards a central point in space, and they're going forwards in time. And remember, time is now along the x-axis, that means they're going to the right. And then when these particles are electron and its antimatter counterpart, the positron, meet, they annihilate, producing a photon. The photon lasts for some amount of time. Here, the photon has a straight line. It really should be a wiggly line, but it doesn't really matter for our purposes. So we have a virtual photon produced, but then the photon to 3 pair production essentially is converted into an electron and positron, which go their separate ways. Now, if we're going to work out the mass of this virtual photon, we need to know again something about its energy and momentum. Well, in this case, the electron and positron we imagine is coming in a kind of head-on collision, meaning that the total momentum before the electron positron went to 0, the total momentum kind of once pair production has happened is 0, meaning to conserve momentum, the momentum of the virtual photon also has to be 0. So our virtual photon has no momentum. However, it does have energy, because essentially the Ras mass has been converted into the energy of the photon, as well as any kinetic energy. But if our electron and positron aren't moving at relativistic speeds, to a good approximation we can just go the energy of the photon is equal to the sum of the Ras mass energies of the electron and positron, because the kinetic energy would be minuscule comparatively. But we have kind of a real positive energy for our photon. And so now we use our relationship to energy, momentum, and essentially what we're calling the effective mass of the virtual photon. We see that kind of, since p is 0 but e is bigger than 0, m squared is going to be bigger than 0. In other words, the mass of our photon is real. So this photon has mass. Real mass, as in not imaginary mass. And you might ask, well, if this virtual photon has if this virtual photon has a real mass, does it actually weigh anything? Does it have any weight associated with that mass? And the answer is we really don't know, because these virtual photons are the products of kind of quantum fluctuations in quantum fields. And so to understand whether there is a weight associated with the effective mass of these virtual particles, we need a gravitational, or in other words, kind of general relativistic version of quantum field theory, or some way to unify ideas in quantum field theory and general relativity, and we don't have an agreed upon strategy to do that yet in physics, so that's very much an open question within the scientific community. But I've got now a challenge and a question for you to help kind of spark some adventures into virtual particles and stuff we've done in this video. Hello, so the last slide of this video, so I've got a challenge for you. I did a challenge on my previous video on full velocity. This is going to be a challenge associated with the content of this video. Now I haven't released a solution to the challenge for velocity yet, because I'm kind of like, adding content to this playlist, and then once I'm at a point where I'm happy with kind of the videos on it, I'm going to pause this playlist at least for a while, and then I'll make a separate playlist containing solutions and discussions of the challenges. But given by this point in the playlist we've covered a lot of relativity, I feel like it's helpful to kind of start stimulating thoughts and discussions through some guided questions. I always would encourage anyone by all means go fully out, explore as many questions as you can, but sometimes it can be a bit overwhelming with there being so many ideas in physics, and it can be hard to know where to go after exploring the topic. So I thought starting with a guided question may help some people. So I've got a kind of challenge or question I'm posing to you for this video. So in this video we, towards the end of it, so let's see t equal 1, we may see a dimensionless or unitless quantity. And my question is, well, if c, the speed of light, doesn't have any units, then what would the consequential units of time and space be? I.e., what units of time and space are consistent with the setting the speed of light to be dimensionless? And I'm asking kind of this question because it will actually link to mass, and therefore to the latter part of the video, and it's helpful playing with different unit systems, particularly thinking about the physical significance of those unit systems. It helps make them not only more easy to remember, but also it's helpful to know the physics behind different unit systems, so you know when it might be beneficial to use one unit system over the other. For example, you could remember the unit system of the Heaviside Lorentz unit system off by heart, but it wouldn't really help you much unless you knew the kind of core thing that's trying to be made simpler by going from standard units to Lorentz Heaviside units. So it's an important skill in physics is to kind of become familiar with different unit systems and their relative advantages and weaknesses. As for this playlist, I'm hoping to do a couple more videos, so one on tachyons, one on neutrino oscillations, so if either of those two sound good to you, stick with this playlist. neutrino oscillation I will involve a little bit of quantum mechanics inevitably for the topic, because neutrino oscillation is the result of special relativity and quantum mechanics together. Tachyons I might include some quantum mechanics. I probably will, because it'll probably be the last video on this playlist for a while. I will put other videos on this channel, but I'm hoping to do more one-off videos until kind of the beginning of December. And with regards to that, I put a poll for this kind of community. So if you go to the channel page and go to the community tab, you will see that there's a poll. And the poll is essentially me opening the floor to you, because I want to make kind of content that you'll find exciting or interesting, and I'm almost spoiled by choice in terms of the amount of wonderful things in physics, so I'm really happy to go, wherever really for, and so I want to really make something that will be of benefit to as many people as possible, and I felt the fairest way to do it was making a poll. And the poll is kind of asking, out of 3 kind of main ideas I have for playlists, which playlist would you most want me to make? And I'm planning to release some videos on this playlist in December. So my ideas for playlists were stellar evolution, general relativity, and also string theory. I did think about making a kind of like mini video for each of the playlists, kind of proposing them and sharing their individual strengths to give you some guidance. However, my own subconscious biases might come through. Personally I would love to do any of those 3 playlists, but I probably do have subconscious biases. I definitely have relative conscious biases, but all 3 sound equally good, just in various ways. But since I don't want to kind of sway the kind of result of the poll, I'll just kind of leave it open to you. And if you'd like to explore more about what those topics offer, there'll be kind of like plenty of videos on other channels or on the web or something. And I'll probably mention more about those 3 kind of at some point in some video sometime, because they're both kind of like quite active areas of physics. So yeah, that's kind of what's happening with kind of this channel for a bit. There's going to be lots of kind of small independent videos separated from playlists. But I'll finish the relativity one for now, and then get on with the individual videos before kind of September kicks in. I'm letting kind of everyone know about the poll in this video, because I want to give people plenty of time to vote or look at what they might want or think on it, or to hopefully get as accurate as possible picture of what would be the most popular playlist to go through out of the kind of 3 options I think might kind of really work for the channel at this time. But as always, I really hope you got something from this video and found it enjoyable. Any kind of comments or suggestions of improvements, please put them in the comments, and I will try to implement them as much as possible in my videos. And I am hoping at some point, it'll probably be around Christmas, but hopefully before then, but we'll see, to get another microphone to help with the quality, and play around with a few editing softwares and that kind of thing. But I hope this video has been kind of enjoyable. I really hope you have a good week. Good luck with kind of exploring kind of the wonderful universe. And as always, hope to see you for another video soon.